Welcome to our presentation on leveraging the power of the portfolio from SIMULIA. SIMULIA is the Dassault Systems brand to simulate product, nature, and life. We have over 1,050 employees worldwide with headquarters in Providence, Rhode Island, with an additional 12 R&D locations focused on deepening the capability we deliver in our product portfolios. We have a very large user community, over 150,000 users covering all industries, many countries, and nearly all roles who benefit from when simulation powers innovation. We have 165 alliance partners who provide complementary technology to expand our portfolio and solutions. And we have a technology-focused strategy to provide high-quality products and support, innovative technology through acquisitions to broaden our offering and increase customer satisfaction. Let's have a look back to the beginning of Abaqus and the early times of simulation. Abaqus was founded by three founders in 1978 in Rhode Island. Abaqus Incorporated joined Dassault Systems in 2005 to become the realistic brand SIMULIA. Since then, our Abaqus technology has been heavily gone through an evolution process with continued enhancement of its solver technology. Also, the SIMULIA brand has evolved through enhancement and acquisition of many different companies with amazing technologies and talented people. In 2008, Ingenious with iSight, 2013, FE Design with Tosca Structure and Tosca Fluid, 2013, Safe Technology with feSafe, and 2014, Simpact joined SIMULIA to enrich the simulation offerings. Finally, just this year, DS announced its intention to acquire CST for electromagnetic simulation. All of the tools shown here are available within the extended licensing of the power of the portfolio from SIMULIA. Abaqus, our proven FEA technology, FEA for process integration and design optimization capabilities, Tosca to enable users to do structural and fluid flow optimization for conceptual and detailed design, and feSafe, allowing users to study fatigue and durability in order to predict and analyze the product's life. We're going to cover three of these products in today's demonstration. Today, the design we'll investigate will be this arm brace mechanism for patients living with partial paralysis or weakened arms. We'll focus our analysis inquiry today on the motor and drive shaft mechanism that operates the arm. We'll break our analysis down into three distinct areas that we want to investigate. Valid mechanism control. First and foremost, our mechanism needs to work, and we need to be able to spec a motor that will operate the arm. Durable operation. Pulley system designs like these can be complex. We want to maintain tension in the belt, but not too little or too much. Durability will also be of utmost importance to our design, so we'll need to understand the belt in detail. Compressive stresses in drive belts like these can lead to fatigue and failure, so we'll pay close attention to the stresses and strains in the belt. Lightweight. Of course, we want to come up with the lightest weight design possible. In this scenario, we'll focus on the gear mechanism. We'll need to have a slot for the cam, but where else can we remove material? We'll find out. As we move through this analysis process today, I want you to think about not only the aspects that we're focusing on today, but other aspects of this mechanism that should be studied using simulation. For instance, drop or impact testing on the shell or operation of the wrist. With the powerful solvers in the SIMULIA and SOLIDWORKS portfolio, everything can be studied before any material is cut. So we're doing this analysis in three steps. We'll start with making sure we have a good understanding of the realistic physics in the problem. We'll take a look at exploring the design by changing some parameters. Finally, we'll see where we might be able to do some weight savings on this design. Let's hop right into our demonstration. Here we have the model of the geometry of the arm right within SOLIDWORKS. What we'll need to do now is bring this geometry into Abaqus. We can do that using the associative interface for Abaqus built into SOLIDWORKS. We're assigning the port. Check to make sure that the SOLIDWORKS install is recognized, and then export the geometry right from SOLIDWORKS into Abaqus to perform our analysis. What we're going to want to do in Abaqus is start by only focusing on the bodies that we're interested in. In this case, the gear, belt, and roller mechanism. So we'll hide different geometry to focus only on those aspects of our design. we're going to go through an already set up model and just review some key aspects of the setup. Here we can see the belt material is applied as rubber. In this case, we're choosing a hyperelastic material and utilizing uniaxial real-world test data to come up with our material properties. Built right within Abaqus, we can evaluate our uniaxial test data in order to figure out exactly what material model is the most appropriate for this rubber. We can see in this plot the Ogden model fits our red test data very well, the Ogden model in green. So that's what we're going to apply to this material model, to the belt. Right within the user interface, we can go to the material property and see that the Ogden model, 3 constants, has been applied to the belt structure. Next, we're also going to add some steel cable reinforcements to the belt. We can specify the geometry and volume of the reinforcements. These are reinforcements laid longitudinally within the belt. Next, we're going to apply contact to our model. Abaqus has a model for general contact that will recognize all the contacting faces within our model and apply a friction condition to them. In this case, we'll want to specify no friction between the belt and the roller designs, but perfect friction through the belt and gears. And general contact allows us to do that. Next, we're going to apply our loads. Here we have a load applied to the output pulley to bring tension into the belt. Next, we can have a look at the torque applied to the model from the arm. And we can see the torque is applied nonlinear over time, and we can see the application curve of that torque. Now, let's have a look at submitting the job. We can submit the job to run on multiple processors and take advantage of the powerful solving capabilities within Abaqus. Once we solve, we can move on to reviewing the results. On first inspection of this design, we've kept the display bodies on, but those weren't a part of the analysis, but they become a part of the visualization technique that we do. And we can see the driving mechanism of the arm. Important thing to note here is because we use the SOLIDWORKS associative interface to bring the geometry right in, if we went back to SOLIDWORKS and made any design changes, we would be able to automatically export the geometry right back into Abaqus and rerun our simulation without having to reset anything up. Here we can see the drive mechanism, just the belt, rollers, and gear. And first thing we might want to look at is the von Mises stress in the gear itself and see if it's below the yield strength in the material. Next, we might want to look at the angular velocity and torque of the motor. This will allow us to come up with the correct sized motor by calculating the power from these 2 plots. And we can see where the maximum peaks are in angular velocity and torque. Next, we can do a nice visualization of our design and have a look at those reinforcements that were placed, those steel reinforcements that were placed within the rubber belt. And we can do an animation of this plot to see how those reinforcements behave throughout the simulation. Finally, we might want to have a look at a contour plot of the principal strain within the belt. What we can see here is we have a relatively large principal strain of about 52%. So that could be an issue for our design in fatigue. In addition, the maximum principal strain, the minimum value, is actually negative. This indicates that we have compressive strain within the belt, which also could be an issue for fatigue within the belt. What we have now is a really realistic representation of our physics, and we can now go about making design changes to our design. Now we just saw how we could use the power of Abaqus to simulate the realistic physics of the problem and ensure the feasibility of the design, as well as identify any problem areas. Now let's see if we can make our design better by leveraging the power of the portfolio to make design changes. Now that we know our maximum first principal strain is too high in tension, and our minimum first principal strain is too low, indicating compression, let's look at some design variables that we might change to get us better results. First, we know that changing the distance between the rollers will affect any tension and potentially any compression within the belt. Additionally, belt thickness and even material properties may play a role in these strains that we're most interested in optimizing. Finally, we'll need to monitor these strain parameters, and our goal will be to minimize the first maximum principal strain to relieve some tension, and to maximize the first minimum principal strain in order to avoid any compression. We can use iSight to automate these design changes in Abaqus. iSight is all about helping users automate and optimize repetitive tasks. Of course, it works with Abaqus, but it also might work with many of your other tools in your toolbox as well. In this example, we'll do 3 different iterations of 3 different variables for a total of 27 different runs. After iSight runs, it collects all of your results and gives you the power to investigate what parameters are most influential on the design. You can immediately view a table of results which shows you the best design as well as other influential designs. Pareto plots give you a sense of which parameters are most important to the results you're trying to optimize. All of the plots can be viewed in many different ways and are automatically created within iSight to give you the confidence and justification for your design decisions. With iSight, you'll always be ready for your design review. By picking just 3 design variables and varying them 3 different times each, we came up with 27 different runs using iSight. Optimizing the roller position, we were able to reduce the maximum strain by 73% and remove any compressive strains in the belt so that fatigue can be minimized. We see the example on the screen, and the design on the right is our optimum design using iSight. With iSight, we were able to completely explore our design space in order to come up with the optimum design for our purposes. Now, let's see how another SIMULIA product might help us remove even more weight from our design. Let's have a look at potentially removing mass from this gear. Where should we start? Should we just cut holes? We can do better than that, but we have to keep a few things in mind. First, we'll need to maintain that slot that allows for the gear to rotate through the support structure like a cam. Second, of course, we need to keep the shaft hole and key. And third, we'll want to maintain our thickness so our belt always stays on the gear. Finally, we'll want to ensure our part is manufacturable. Let's see how we can take all of these into account with Tosca from SIMULIA. Tosca optimization software within Abaqus is going to allow us to use the software to tell us where it's appropriate for us to remove material from our design. We're going to start with the complete design space or full complete geometry, and we're going to let Tosca tell us where we can start to cut some holes. In this example, our full gear analysis and loading conditions are coming right over into this gear model in Tosca. So we can see we have our belt load. We're also going to have some surface traction coming from the belt loading conditions. And in addition, we'll have some torque that was applied from the arm and the motor. All of those loads come right in from our previous analysis. Next, we're going to set up our optimization task using Tosca. In this case, we're going to be doing a topology optimization, but Tosca has the capability to do shape, sizing, or even bead optimization. When we first create our Tosca study, we're going to set up some different settings. For instance, we'll freeze different loading and boundary regions, and there's lots of different other settings associated with the optimization that we're going to do. We're going to leave a lot of them as default and change one to a condition-based optimization. Next, we're going to set up the design responses that we really want to monitor, the first being the strain energy of our design. This is going to ensure that as the material is removed, strain energy is kept track of so that we know that our stiffness can be maintained. We're also going to set up a design response for the volume of the material because we want to remove as much volume as possible or keep that as low as possible. So we're setting that up here. The next thing we're going to do is we're going to set up our objective functions. In this case, we want to minimize the strain energy in this design in order to maximize or maintain the stiffness of the design. Next, we're going to set up our constraints of the design. In this example, we're going to want to remove as much volume as possible. We're going to try to take out up to 70% of the volume within this design. Next, we're going to set up some geometric restrictions so that Tosca doesn't remove material where we don't want it to remove material. We're going to set up so-called frozen regions of the model so that Tosca only stays outside of these frozen regions. You can see we're selecting the geometry around the shaft and key because we want to maintain that geometry. In addition, we're going to select the geometry around the cam. Again, we don't want Tosca to remove that cam. That cam needs to be there to maintain the area where that bolt structure goes through to support the design. In addition, we're going to freeze the region on the outer edge of the belt. Again, we don't want to remove any material because that material around the edge of the design is supporting the belt structure, so it can't be removed by Tosca. Next, we're going to set up additional geometry restrictions. We're going to invoke a symmetry condition so that the Tosca optimization is done rotationally symmetric about the axis. In this case, we're going to shoot for 30-degree segments, or about 12 spokes in our design, potentially. Additionally, we're going to set up some demold control in our design. This is going to take into account the manufacturability of the Tosca optimized part. We want to make sure that the manufacturability of this part is maintained no matter what Tosca chooses to remove material from. You can see here we can take into account different manufacturing processes and make sure that Tosca comes up with the right manufacturable part. Here we're specifying the split plane for this particular part so that Tosca knows it can't create any undercut sections in this model. Lastly, we're going to set up some thickness control in this design to make sure that the belt area doesn't get removed, and also the thickness of the belt stays the same so that the entire belt can fit on the gear itself. So we'll enter a minimum thickness that Tosca can make that, and that's the thickness of the belt. Now we're going to set up the optimization run. We're going to allow for Tosca to do 60 different cycles, each time figuring out the strain energy and volume of the design and removing material where it's necessary and allowing the material to be maintaining the stiffness of the design. From here, we can go ahead and validate our design and submit our job to run on as many processors as we have tokens for. We can see our digitally optimized design, and we have a nice kind of looking organic shape with different spokes around the outside of the geometry and then different slots around the design. Knowing this, we can move to SolidWorks and then actually just go ahead and create this design. We can see the spokes we created as well as those slots according to the Tosca optimized design. Additionally, the thickness on the inside there is thinner than the belt section. So we really were able to remove a significant amount of material. Using the associative interface for Abaqus, we can export this geometry right back to our model and do a validation run and have a look at the results. Here we can see that the stiffness is maintained and the stress in the material is still below the yield strength of the material. So we have come up with a valid design which reduced a lot of weight from this design. Here we can see our initial design on the left and our final design on the right. If we compare the volume from the initial design to the final design, what we see is over a 53% weight reduction from the initial to the final design. We know that this is going to be the best design for us because the software told us where to remove material and ensure the reliability and stiffness of the design. We use Tosca topology optimization in order to reduce weight in the design. The software decided where it was the right place to remove that weight. Instead of us cutting holes randomly in that gear, we know this, by using the software, we're removing the material in the right spot. Now, if we remember what our goals were when we started, we wanted to start with valid mechanism control. And using Abaqus, we not only ensured we had a working design and were able to size the motor, but we identified problem areas within the strain in the belt of the design. From there, we wanted to ensure that there was durable operation of the design. iSight and the power of the portfolio allowed us to automate design changes and automate the results processing in order to guide us to the best design, so that when we went to a design review, we would be able to justify all of our decisions and have the data to back it up. Finally, we used Tosca to create a more lightweight gear of the design. The topology optimization using Tosca reduced the weight of the gear by more than 50% versus the original design. If we invite advanced simulation into our design processes, we can make our lives easier and truly realize innovation.